All right, so we are on chapter 7 and we're doing section 2's odd numbers in our in-class problems. Okay, explain the difference between a covalent bond and an attractive force. If you remember why it's called a covalent bond, co meaning more than one, right? At least two. Valent is referring to our valence electrons, right? So what is it really? It's the sharing of electrons between two atoms. And this is really, by definition, a chemical bond, right? Attractive forces are not chemical bonds. They're not. So an attractive force is a force. It's not a bond. So this is an interaction between positive and negative areas of different molecules. So this is no shared electrons, right? So be careful that you understand the difference between that, okay? Explain the difference between the dipole and London dispersion forces and the dipole and dipole-dipole interactions. So if you are doing London forces, these are temporary, right? Remember we said if you had some molecule like this and it had a particular electron cloud that looked sort of like that, right? If it bumps into a wall, like here's the wall, and it bumps into that wall, what's going to happen? Well, you still have the same elements, right? But this electron cloud ends up kind of larger on one end than the other, right? And so you have an area that ends up being negative because you have all these electrons, right? All these electrons that are hanging out, and then you have a positive end. And so the London dispersion forces are temporary, whereas the dipole-dipole interactions, right? Dipole-dipole interactions are permanent, right? You have oxygen, you have hydrogen. Well, what are the electrons doing? You have a really small, you really have a small electron cloud around the hydrogens, but then around the oxygen, oh, you got a big electron cloud. So you got a lot of electrons hanging out over here. So this is negative, this is positive, and this is positive. And so the dipole-dipole interactions, these are permanent, right? Whereas London dispersion is temporary, okay? Let's see. Oh, yeah. I wanted to answer this. What is a hydrogen bond? I added this. A lot of people get this wrong, right? What is a hydrogen bond? It is an attractive force. It is the strongest dipole-dipole interaction. Right? It's not a bond. We say hydrogen bonding, and I would just like to shake the person who named it hydrogen bonding, but it's just a dipole-dipole interaction. So hydrogen bonding, or a hydrogen bond, is an attractive force, right? Force between what? Between a hydrogen and a polar bond with, remember, it's no fun, NOF, nitrogen, oxygen, or fluorine, right? So the hydrogen would be the donor, and then either it's nitrogen, oxygen, or fluorine are going to be the acceptors, right? And they need a lone pair in order to be those acceptor, right? Like water, right? So hydrogens here are the donors, And then this oxygen has 2 lone pairs. So this is one acceptor and this is one acceptor. Okay. All right. Okay, explain the requirements for a molecule to be a hydrogen bond acceptor. Not a donor, an acceptor. It must have a lone pair of electrons on nitrogen, oxygen, or fluorine. Okay. All right, 7.23. An ion-dipole attraction often occurs when ionic compounds mix with water. Why do you think this is so? Right? This is our example. Our example is salt, NaCl, dissolves in water. So why do we have an ion-dipole interaction? Well, because ionic compounds have what? What are they composed of? We have a cation. A cation is what? Positive. And an anion. An anion's negative, right? So the 2 ions basically become hydrated. So they split apart because instead of being attracted to just one of the oppositely charged ion, there's all this water that's hanging around that's got this partial positive and negative charge. And so the water molecules surround the ions, breaking them apart. Right? So how does it do that? Well, the partial negative on water's oxygen, right, attracts the cation, and the partial positive on water's hydrogen attracts the opposite charged anion. Opposite charges attract. Pretty nice, right? Okay, identify the strongest attractive force present in the pure substances shown. Are they London dispersion, dipole-dipole, hydrogen bonding, ion-dipole, or ionic interactions? You can use the flow chart. I put it for you, but I'm not going to. I'm going to try and not look at it, okay? NAF. If you kind of look at what kind of a molecule this is, it's going to tell you the answer. So what kind of a molecule is sodium? Sodium is a cation, right? It's a metal, so it's going to form a cation. Fluorine, non-metal, that's going to be an anion. A cation and an anion, that is an ionic compound, right? So that's going to be an ionic compound, right? So ionic interactions. All right, B, CH3, CH2, CH3. This is nonpolar. It is just hydrogens and carbons. So what kind of force? That's London forces. All right, CH3NH2. So you might have to draw this one out. CH3NH2. Well, what do we have on that nitrogen? We got a lone pair on the nitrogen, right? Well, that can interact with another molecule of the pure substance. And so this is going to end up being an acceptor. And then you'll have another molecule, right? That'll be a hydrogen, a nitrogen, hydrogen, CH3, right? So then you end up with this interaction like that. And there's your hydrogen bond. So here is, let me change this back. Here's your donor, here's your acceptor, and there is the hydrogen bond right there. So this would be hydrogen bonding, okay? The last one, CH3F. Well, CH3F, if you draw this out, right, that's carbon, 3 hydrogens, and a fluorine. Fluorine's gonna have 3 lone pairs on it. So this one can actually have a negative charge. So if you look at the overall polarity of this molecule, it's going to be a polar molecule. Fluorine the floozy, she is going to want those electrons, right? So this is a polar molecule, but do you have hydrogen bonding? I don't have a hydrogen that's associated with no fun, a nitrogen, a fluorine, or an oxygen, right? We have hydrogens and we have fluorine, but the hydrogen is not bound to the fluorine. So we don't have hydrogen bonding. So no hydrogen bonding, B-O-N-D-I-N-G. So this would be dipole, dipole. Dipole, dipole. So that's D. D is dipole, dipole. Okay. All right. What about that? Going to go down. How many hydrogen bonds are in CH3NH2? How many hydrogen bonds can CH3NH2 make to water? Draw them. Okay, so CH3, and that's bound to a nitrogen, and that nitrogen is bound to 1, 2 hydrogens. What else is on the nitrogen? Complete its octet. All right, now, how about water? What's going to happen with water? Well, what I can see here is that this is an area that could participate in hydrogen bonding, right? And I also see that I have a hydrogen bound to a nitrogen. So this is an area that can interact. So this would be, for example, a acceptor site, and this would be a donor site. So how would I draw my water molecule in? Well, I need a donor, right? And so I'm going to end up with a hydrogen bond. Usually they draw hydrogen bonds as red, but I've already got them in red, so let's do green. And they draw them as little dashes, right? And so here's one hydrogen bond, and then we're going to have water, but in this case, now it's going to be the oxygen, because we have those two lone pairs. I guess I should kind of draw them like you have one here, you have one here. So this one's going to interact. Oh, I should have been drawing that in blue. Doesn't matter. But you have a dash. So here's a hydrogen bond here and here, right? So how many can it have? Well, be careful. I have another hydrogen here. So this other hydrogen can also act as a donor. So then we need another water molecule. So here's my oxygen. And this has those lone pairs on it. And so we're able to make a hydrogen bond here. So let's go ahead and draw that in as little dashes, right? So now we have 3 hydrogen bonds with water, right? Those are our circled. 1, 2, 3 hydrogen bonds, okay? All right, predict which pure substance will have a lower vapor pressure, water or ethanol. Explain your answer. Well, remember, with water, we said how many different areas could you have? Here's an acceptor, here's an acceptor, here's a donor, here's a donor. So I know I have 4 hydrogen bonding possibilities here. Okay, let me look at my other molecules. CH3, CH2, OH. So how many do I have? Okay, well here I have 2 sites that can be acceptors. Oh, but I only have 1 site here that can be a donor. So this one is going to make 3 hydrogen bonds. So which one's going to be stronger? Well, the one with the more hydrogen bonding, the one with the stronger interactions, is going to have, so let's write that down, stronger interactions, stronger or more interactions. Either way, you're going to have a higher boiling point, you're going to have a higher melting point, and you're going to have a lower vapor pressure, right? That was what I told you to remember from the lecture. So what's our answer? Our answer is water. Water is our answer, lower vapor pressure. Okay. Predict, oh no, we're doing 3-1. Rank the following compounds in order of increasing boiling point, lowest to highest, and explain your ranking. All right, I am gonna number these A, B, and C, just so like I can talk about it and it's not confusing for you. So when we look at these, what do we have? We have a straight chain alkane. We have a branched alkane. Now ALK, oh my goodness. ALKANE. Let's see how many carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so they have the same number of carbons. So these are both undergoing just London forces because they're both non-polar, so we just have London forces. So which one has more surface area? A is going to have more surface area. All right, so let's kind of just keep that in mind. We're going to go on to C. C, oh, what do I have over here? We have an alcohol, right? So this alcohol is going to have lone pairs on that oxygen. So I can participate as 2 acceptor sites and a donor site. So this is going to be hydrogen bonding. If I have hydrogen bonding, this is going to be my strongest. So I'm going to write strongest here. So C is going to be my strongest. Then I got to think, okay, where's my weakest? My weakest is going to be my branched chain alkane because it has less surface area. So this is weakest because it only has London forces and has less surface area for interactions. So I need to rank them from order of increasing boiling point. So we're going to go lowest to highest. So our lowest is going to be B, and we're going to highest. So it'll be B, A, C. So this is, I don't know why I kind of put it over there, but that should be our order, B, A, C. Okay, all right. 2 common inhalation anesthetics, desflurane and servoflurane, have vapor pressures of 699 millimeters mercury and 170 millimeters mercury at 20 degrees respectively. Which one is predicted to have a higher boiling point? So remember, if it's stronger, whoa, stronger or more interactions, you're going to have a higher boiling point, a lower vapor pressure, and a higher melting point, right? So what did they tell us? They told us that our first one, desflurane, so has a vapor pressure equal to 669 millimeters mercury. Then our other one, whoa, has a vapor pressure of 170 millimeters mercury. All right, so now we kind of have to think backwards just a little bit. So if we decrease our vapor pressure, right, a lower vapor pressure is telling us that, that we're going to have a higher boiling point, right? You have to remember this. I'm telling you, you have to remember this. Put this on your cheat sheet. It is not on the equation sheet or anything like that. So you do have to know this one, right? Okay. Oh, and that's it. Yay. All right. Y'all have a good rest of your day.